So here we're going to calculate the magnetic field of an actual solenoid, just as an example. So I wrote the equations that we need here. This, we derive from Ampere's law, where little n is a turns ratio. That'd be capital N over L. And mu naught I wrote down twice. There's two reasons I wrote it down twice. This is kind of just a standard value in scientific notation. However, the one beneath it is actually exact. So again, this has some rounding errors and whatnot. But just by definition, this is exactly equal to mu naught. It is exactly this number, 4 pi times 10 to the minus 7. But, again, we know mu naught to a lot of, enough precisions that we don't really have to worry about accuracy. So the fact that this is exact doesn't really concern me. But sometimes, like in that example of the straight wire, where B would be mu naught I over 2 pi r. In that case, if you plug in mu naught as 4 pi times 10 to the minus 7, and in the bottom you have 2 pi, you get some cancellation. So sometimes it's just more convenient to use that version. But here, I want to focus on, say we actually build a solenoid. And so I have one right here. So I'll hold this up a little bit. You can see it's like one wire that's just wrapped around the cylinder, just a cardboard cylinder, wrapped around over and over. And so we want to calculate the magnetic field. Now, the difficult part, we can measure the length, and we need the length. The number of turns I sort of counted. There's about 220. I can't say that number is exact, but I kind of just counted like a certain length and then multiplied. But so we'll say there's 220 turns. I can measure the length of the solenoid. It's about 15.5 centimeters. And then we need to know the current. So let's say we hook this up. Say we have a 12-volt battery. So we have something that looks like this. Like, here's our solenoid. And if we hook this directly up to a battery, there's a little bit of resistance in the wire itself. That could be a significant amount because there's 220 turns, and it's not a very wide cylinder, but that circumference is a couple centimeters. So the actual wire that went into this, 220, this is several meters long. So let's just say, to make life simple, let's say we have a 12-volt battery, and let's say the resistance of the wire is 1 ohm. And in that case, the current is just V over R. So the current going through our solenoid would be 10 amps. So if I hook this up to a 12-volt battery, if the resistance was 1 ohm, I could calculate that more exactly. I believe this is just copper wire. But, or say we could add a little extra resistance if we want. But, say we get 10 amps going through this. And now let's calculate the magnetic field inside this solenoid. Okay, so we have B. Now, mu naught, there's not going to be any pi in our, anywhere else in the problem. So I use this top value, 1.26 times 10 to the minus 6. Okay, so Units, Tesla meters per amps, 1.26 times 10 to the minus 6, so that looks good. Now we've got N is 220 divided by 15.5 centimeters. So that'd be N over L. And then times 10 amps. And we need one conversion factor. 100 centimeters is equal to 1 meter. So let's simplify this a bit. Let's look at the units first, and then I'll erase it. Just going across, let's just do it like this. Meters cancel, centimeters cancel, amps cancel. This will give us the magnetic field in Teslas. So 1.26, I'm going to round that off to 1.3. And then I'm going to say 2.2. So here we've got, 2.2 times 100, that's 10 squared. So that'd be 10 to the second, 10 to the third, 10 to the fifth power. So that's what we have on top. And on the bottom, I'm going to say this is 1.6 times 10 to the 7th power. So a little bit of rounding off. Here, 1.3 on the bottom, let's just say 1.6. And here we have 10 to the, so I took 10 out of here, so that's 10 to the 7th power. This is going to give us kind of a small number. So let's say 10 to the 3rd milliteslas per Tesla. So if we simplify it a little more, got let's do 1.3 over 2 times 2.2. It's about 3.9 divided by 1.6. And then we have 10 to the 8th over 10 to the 7th. So basically we have 39 over 1.6 milliteslas. That's going to be around 20 something. Let's see. I think it's here around 2.4. Or sorry, 24. Can't check something. Yeah, that's about right. So, what we get for this particular solenoid is around 24 milliteslas. So if we take this solenoid and run 10 amps through it, the magnetic field inside would be around 24 milliteslas. I want to compare that number to something. Yeah, I've got a table here. Magnetic field. It says a large electromagnet, that would be 1 Tesla. A small bar magnet would be 10 milliteslas. So, yes, you just have like an ordinary bar magnet that kind of you get at a store. That would be around, a little less than half of what we'd get by running 10 amps through this. And again, this depends on the current. So if you run a very small current, you get a weak field. You could just keep increasing the current, but again, wires have limits. Depending on the wire, you can't run too much current through it or they overheat and melt. So that could be a bit of an issue. But yeah, so that'd be the magnetic field inside a solenoid. Actually a fairly straightforward calculation. I mean, kind of cool to run 10 amps through this, but the problem is it's kind of hard to measure the magnetic field strength. Probably a good way to do that would be like with torque. Like have an object that can rotate with the field and have it kind of like on a spring, so the more force you apply, the more it's going to twist, and you can measure that twisting. But it'd be hard to fit that inside here and be able to see it. So if there's a way to actually measure the field, I would just run a current through it and test that, but yeah, I don't know how to measure the field experimentally inside this solenoid, so just compare it to a bar magnet, and the answer seems pretty reasonable. Okay, so yeah, I think that's it for this magnetic field of a solenoid. All right, yeah, that'll be it. Next, we're going to talk about, we're going to combine a few things. We're going to talk about, like, say we have two wires carrying currents. They're going to exert forces on each other. We'll talk about that next.